Well, hello everyone, good morning. Thank you for making it here so early. Okay, so I'll start the week. So my lecture will be on non-invertible symmetries. And I haven't watched all the video recordings from last week, but I think Clay and probably many others have mentioned non-invertible symmetry. So let me be a little bit more specific. In my talk, I will mostly talk about non-invertible symmetry on the lattice. In fact, just for a bunch of qubits. So this is to be contrasted with what Clay talked about last week, where he focused on continuum field theory. Now, this is a lecture at the school, and this is a Blackboard talk. So that means I won't be able to provide comprehensive references for all the papers that are related to these lectures. And I apologize in advance for that because there are many experts in the audience who have done related works. Most of my lecture, the first half of my lectures will be based on my TASI lectures from last year. And in addition to that, I will mainly follow, for the first half, I will follow these two papers. And then in the second half of the lectures, I should say that many of you probably have already heard the first half. I'll try to add more details. But for the second half, I will follow a paper I wrote with, I don't have the archive number. All right, so that's kind of the organization. All right. Yeah, so as the title suggests, I will talk about a new kind of symmetries that are known as non-invertible symmetries. And the name sounds paradoxical because ordinary symmetries follow the paradigms of Wigner's theorem. And Wigner's theorem states that in quantum mechanics, every symmetry should be generated by a unitary or anti-unitary operator. And unitary and anti-unitary operator, by definition, have an inverse. You take the operator U dagger is its inverse. But in recent years, there has been a lot of development in both quantum field theory and in lattice system, where it has become increasingly clear that the notion of symmetry should be generalized the moment we depart from quantum mechanics, when we go to quantum field theory in general space-time dimensions, and when we go to lattice system and many-body system in diverse dimensions. And among all the generalizations, some of them are implemented by conserved operators that do not necessarily have an inverse. And there have been several examples on that. And personally, there are a few examples that I like. And depending on your background, you might find some of them more appealing than the other. I would say maybe the first example, well, let me not say first, but one example that has been known for many decades is the non-invertible symmetry in the 1+1 dimensional Ising conformal field theory. And just to make it clear, for my lectures, whenever I say CFT, I really mean in the continuum field theory, rather than some critical lattice model. So 1 plus 1D Ising conformal field theory is arguably the simplest possible quantum field theory of all. We're in the lowest dimension possible for quantum field theory. Ising conformal field theory is the first minimal model. It has the smallest possible central charge, namely degrees of freedom, among all the unitary conformal field theory. And already in the simplest possible conformal field theories, there's a non-invertible symmetry. Now for Ising CFT, there's a defined Z2 symmetries, which is a conserved operator that will denote by eta. It's a Z2 symmetry, meaning that when you squares it, it equals 1. This is almost the defined symmetry of the Ising model. When you try to realize the Ising conformal field theory microscopically via some lattice spin system, the Z2 symmetry flipped all the spin from up to down. We'll see more of that in just a minute. But at the CFT point, there's another conserved operator. It commutes with the stress energy tensor. However, it does not have an inverse. That operator I will denote by D. And the operator algebra, this D satisfied together with eta, takes the following form. So already from here, you see that D cannot possibly have an inverse, because if it did, then you can multiply D inverse on both sides, and you will conclude that the Z2 operator is a trivial operator. But that's a contradiction, because in the full-fledged CFT, eta is a non-trivial operator that acts within the CFT. The more interesting algebra is when you take D squared, equals to 1 plus eta. Now, in my lectures, I'm not going to spend too much time on the Ising conformal field theory itself. And it's perfectly fine if this is the first time you see these equations. But I would guess that this equation should be familiar with for people who have studied conformal field theory in one form or another. It has appeared in many different places, and this is one of them. The following lectures will be self-contained, and in a way we will rederive these expressions from the microscopic point of view. And you might like this example, if you are a bootstrapper. Or if you are a string theorist. Or if you come from other backgrounds. So that's one very nice examples of non-invertible symmetry, which, again, let me emphasize, already exists in the simplest possible quantum field theory of all. Now the second example, which I believe was covered by Clay last week, is the non-invertible chiral symmetry. In the ordinary 3 plus 1D QED. To be more specific, I really meant the ordinary U1 gauge theory coupled to a massless Dirac fermion of unit charge. So it's a limit of the real-world QED describing our electrons, photon, and positron, etc. This example was discussed much more recently compared to the one in Ising CFT. This one was known for decades, and this one was only discussed from 2022.
Okay, chiral symmetry means U1 symmetry with anomaly something.
Yeah, so I wasn't planning on saying too much about it, but yeah, since you asked, let me say a little bit more about it. So in QED, let's say psi is a Dirac fermion. I'm using the 4-component notation. Then classically, the Lagrangian has a axial U1 symmetry that maps psi to e to the I alpha over 2 with the important factor of gamma 5 times psi. Here alpha is the rotation angle ranging from 0 to 2 pi. And as Shu-Heng commented earlier, the reason I put the U1 in quotation marks is because this chiral symmetry U1 has a famous Adler, Bell, and Jacqueff anomaly. And the usual interpretation of the anomaly is that a classical global symmetry fails to be a global symmetry quantum mechanically. Now in 2022, in a pair of papers where it was reinterpreted that this classical anomalous global symmetry is actually not completely broken by the ABJ anomaly. The new interpretation is that it becomes an exact non-invertible global symmetry. Yeah. Okay, I should really watch Clay's lectures before I talk here, but I didn't have the time yesterday. But when I coordinated with him our lectures, I believe he said he will cover this. But anyways, I probably, oh, he did, okay, great. But I won't talk about this example, but I will say this example will probably be more appealing to you if you come from maybe particle physics background or from the quantum field theory background. Great. So these are two very nice examples of non-invertible symmetries. One exists in really the simplest quantum field theory of all, and the second in a very important quantum field theory that describes a limit of our real world. But if you ask me, what would be the simplest example of a non-invertible symmetry that hopefully you can teach to an advanced undergraduate student, then probably both of them are a little bit too advanced. So the third example, which will be the main focus of the first half of my lectures, will be what I personally consider to be the simplest example of non-invertible symmetry. And that's closely related to number one, and that's the non-invertible symmetry in the Ising lattice model. And let me add more adjective here. Again, I'm in 1 plus 1D, but this time I'm working with the lattice model. Now, the word lattice can mean several different things to different people. So let me also be a little bit more specific here. For my lectures, I will talk about Hamiltonian lattice model. In many literature, it's also known as the quantum lattice model. So quantum / Hamiltonian. This means that my space will be discrete. It's made out of discretized qubit, but my time will be continuous, described by some Hamiltonian evolution. There's also a version of this using the Euclidean Ising lattice model, but I will not talk about it. All right, and this model also has another name, which is just the transverse field Ising model. So I will focus on these examples. So the setup is the following. As I said, the space is discrete. So my space is a periodic circle.
Yeah. Before you go for this, how do you think about rep G symmetry? That rep G symmetry will be not good example for some reason.
That's a good question. Yeah. So let me get to that. Yes. In fact, that's the second half of my lecture. Yeah. But let me say a few words about it. So rep G is a good example. I mean, I like it very much. In fact, I think maybe 2 years ago, I would say that's one of the simplest examples. But somehow in the past 1 or 2 years, I came to like this example better. One reason is the following. One reason is that the construction for the non-invertible Kramers-Wannier symmetry in the Ising model has a more natural, when you generalize this to general space-time dimensions, this will lead to a non-invertible symmetry that acts on the entire space. So in the fancy higher form symmetry language, that would be a non-invertible zero-form symmetry. If you generalize rep G to general space-time dimension, that would be a non-invertible higher form symmetry. Yeah. But indeed, in the second half of my lecture, we will see the rep G. Yes. Okay. Any other question at this point? All right. So the setup is really simple. We have a periodic lattice, and I have site labeled by J equals to 1, J equals to 2, all the way to J equals to L. And throughout, I will always work on a periodic lattice. So J will be identified with J plus L. And on each site, I have a local Hilbert space, which is isomorphic to a two-dimensional complex space. So that's just a mathematical way to say that I have a qubit on every site. And my total Hilbert space, H, is simply a tensor product of all these local Hilbert spaces. So in particular, the dimension of my Hilbert space is 2 to the L. All right. And on each local qubit, I have a pair of local operators, xj and zj. Those are the Pauli matrices. They satisfy the ordinary algebra. And of course, you can get yj by multiplying z and x with a factor of I. Okay, so that's the Hilbert space. And importantly, this is a tensor product Hilbert space. It means that the Hilbert space is a tensor product of local factors in space. And for most of the statement I'm going to make during the following lecture, it will be true for any finite L. So I don't necessarily have to take the infinite L limit, but of course, to compare with the continuum field theory, sometimes I have to. And to talk about different phases of matter, I also have to take the L goes to infinity limit. But all the operators I'm going to present, they exist for finite L. So for any finite L, this is just a finite dimensional vector space. And all the operators we're going to talk about, they're just some big 2 to the L by 2 to the L matrices. And you can literally verify all the equations they satisfy explicitly, say, on Mathematica. All right. So I have given you the Hilbert space. It's just some finite dimensional Hilbert space system. And now I want to specify the Hamiltonian. So space is discrete, but I have a Hamiltonian describing the continuous time evolution. Okay. So this is the Hamiltonian that we will focus on. It depends on a continuous parameter G. Now, why do I care? Why do we focus on this Hamiltonian? This is the leading order Hamiltonian if you impose the following ordinary symmetries. So the first symmetry is just the defined symmetry for the Ising model, and that's a Z2 symmetry. So in my convention, I will use 0 and 1 for the Z basis. So I'll use 0 and 1 for, as eigenstates for the Pauli Z matrix, and I'll use the plus and minus as eigenstates for the Pauli X matrix. You can think about 0 as pointing up, 1 as pointing down for the Ising spin. And the defined symmetry of the Ising model is a Z2 symmetry that flip all the spin from up to down. So in this convention, it has to be the X operator. So each xj will flip 0 to 1 and 1 to 0, vice versa. Now this is a very ordinary symmetry. Each xj squares to 1. Xj's at different sides don't talk to each other. So we obviously have eta squared equals 1. And such a symmetry, as I think Max discussed last week, has a simple name. It's known as an on-site symmetry. It means that you can write it in terms of local unitary operators at every site, and each local unitary factor realizes the symmetry linearly. Indeed, each xj squares to plus 1. So that's the linear realization of Z2. Okay, so there's nothing special about the Z2. There's a second symmetry we would like to impose, and that's the lattice translation. And I'll denote it by T. So what T does is that it translates the index j by 1. Now, if you impose these two symmetries, this is the leading order Hamiltonian you can write down. It's translationally invariant because you sum over j, and you impose the Z2 symmetry. X is Z2 even, Z is Z2 odd. So you write down linear terms in X, you write down quadratic terms in Z with the nearest neighbor interaction, and that's it. Right. Now, this Hamiltonian gives the simplest example of a second order phase transition between the symmetry breaking phase and the symmetry preserving phase. So as you take L to infinity, the phase diagram looks like this. When G is large and positive, this term dominates, and all the spins will be pinged to the O plus product state. So right over here, you will have plus, plus, plus here. And this is a Z2 unbroken phase. You have a unique ground state, and under which the Z2 symmetry leave it invariant. So in particle physics language, if you realize this as a lambda phi 4 theory, the potential looks like this in this part of the phase diagram. When G is very close to 0, then this term dominates, and then all the ground states are the product states of 0, or all the product states of 1. So this is like the O spin up or O spin down state. And in this phase, Z2 is broken. And in the lambda phi 4 language, that corresponds to such a potential. Now for these two phases, they are gap, meaning that as you take L to infinity, the difference between the ground state and the first excited state remains order 1 as you take the limit. Now right at G equals to 1, there's a second order phase transition between the two phases, and that's described by the Ising conformal field theory. Okay. All right. Any questions so far? I think everything I said so far can be found on Wikipedia. Yes?
In phase diagram, okay, is the coefficient of the ZZ a different G, or is it?
So this is G inverse, and these are...
G prime, sorry.
Oh, sorry. Yeah. Okay, so the overall scale of the Hamiltonian doesn't really matter. What we really care about is how the gap scales as a function of L. So if you multiply it by 7, I don't care. So up to an overall scale, it's only the relative coefficient that matters, which for my convention, I take it to be G squared. Yeah. Any other question? Okay. So everything I said so far is completely standard. Now the question we would like to post is the following. We know at G equals to 1, in the L goes to infinity limit, it becomes the Ising conformal field theory. And in the Ising conformal field theory, it's known that there is an additional conserved operator D. This D, first of all, is self-adjoint. So D dagger equals D. So it's very natural to ask, if you take finite L, but sitting right at G equals to 1, do we have such an additional or enhanced symmetry operator, even on the lattice? Now, there doesn't have to be. The symmetry can be emergent, but maybe it's already there on the lattice. So the question is, at G equals to 1, and finite L. Is there an operator such that, and let me just write down what I require about this operator in the following. Well, maybe I should call this 0. The zeroth order requirement I would like to impose on this operator is that it acts within my Hilbert space. Right? That's what I usually mean by an operator. I don't want a map that takes me from one Hilbert space to a different one. I really want an operator acting within the same Hilbert space. And that should be implied by the word operator, and that's why I call this the zeroth condition. So it acts within the Hilbert space H. And throughout, I'll only have this one single Hilbert space, which is 2 to the L dimensional. There will be some intermediate steps. I make it a little bit larger or smaller, but the final conclusion will always be about operators in this 2 to the L dimensional Hilbert space. This might look like a very innocent assumption, but this is actually the requirement that's typically being relaxed in some discussions. Okay. Now, the next requirement I would like to impose is that I want it to be a symmetry. I mean, that's what this summer school is about. Now, we can spend all day talking about what the symmetry is. And I think we already had a whole week of discussion last week. And people have different opinions on what symmetries should be. And people getting to fight about it. But I think at the very least, when we talk about, say internal symmetry, for example, we want the symmetry to commute with the Hamiltonian. Right? If something commutes with the Hamiltonian, that leads to a conserved quantity. That's not a sufficient condition for something to be called a symmetry, but at least it should be necessary. For space-time symmetry like Lorentz boost, it may not commute with Hamiltonian. But for the symmetries that I'll be interested in my lectures, it will commute with the Hamiltonian. So I want the operator to commute with the Hamiltonian. Okay, so my curly H is the Hilbert space, my ordinary font H is the Hamiltonian.
So can I ask a question?
Yes, please.
Which may not be applicable in this particular scenario, but do we want it to actually commute with Hamiltonian or be time independent? For example, if it has explicit time dependence.
So, yeah. So here I work in the quantum lattice formulation. Right.
More general as a symmetry, like do we mean commuting with Hamiltonian or being time independent?
I think more generally, at least for internal symmetry, they will be equivalent.
Well, if I have explicit time dependence, right?
Right.
Let's say in current output or something.
Maybe I didn't follow the question exactly. Okay, yeah. But in the Hamiltonian lattice formalism, the time evolution is specified by the Hamiltonian, and that's the condition I'm requiring. Yeah. If you're working a Euclidean lattice model, then the condition you would like will be something like it's topological. Any other question? Okay. All right. So the final condition I would like to impose is that I want this operator to flow to that curly D as I take L to infinity. So I want it to become this curly D when L goes to infinity. Okay, the final condition is a little bit hard to make precise if you don't know what that curly D is. But hopefully, following the presentation I'm going to give, it will become clear that the operator I will present satisfies these conditions. Okay, so is the formulation of the question clear? It's basically asking at G equals to 1, do we have an enhanced symmetry?
Yeah. So for Ising CFT, it is kind of integrable, so it has infinite symmetries.
That's right.
Do you expect other symmetries to?
That's right. So that's a good question. So that's the reason I have to add the final requirement there. Otherwise, I can use the transfer matrix to build infinitely many conserved quantity. Indeed. So, I can just excuse myself by requiring the second condition over there. But more importantly, there should be a notion of locality associated with the symmetry we're discussing here. And that really there are two ways to say it. One way is to say that you want the operator to act in a reasonable way on the local operator. Now, but I have to say a lot about what I meant by reasonable. And we'll see that this operator acts in a nice way. If you take some arbitrary operators that commute with the Hamiltonian, for instance, you can do a projection to some energy eigenstate. That operator will be made out of the Hamiltonian, and therefore it commutes with the Hamiltonian, but it won't act in a reasonable way on the local operator. That's one way of saying it. The second way of saying it, which I personally prefer, is that in continuum field theory, this operator, you can treat this curly D as an operator acting on the Hilbert space. But by changing your time and space direction, you can also view it as a defect. So it's important that the symmetry leads to a defect that's localizing space. And you want to impose the same thing for a symmetry in a quantum lattice model. And the symmetry that I'm discussing here does correspond to a localized defect. But if you take an arbitrary conserved quantity in the Ising lattice model, that won't be the case. Yeah. But I probably won't have time to talk about the defect on the lattice. Any other question? Yeah.
Why can't you just say that whatever it is satisfies those equations over there, or is that equivalent to what you mean?
So, in fact, as we will see later on, you won't be able to find such an operator. Technically there is, which I will mention, but it will not act in the same way. You will see that algebra will be slightly deformed on the lattice. So I cannot say that. So rather I have to say that second condition in a convoluted way. All right, any other question? Okay. Now, many people's first reaction to this question is that, of course, there's a symmetry at G equals to 1. And that's the Kramers-Wannier transformation. So what is the Kramers-Wannier transformation? It's a transformation that maps xj to zj plus 1 and zj plus 1 to xj plus 1. Okay. Now, clearly, at G equals to 1, your Hamiltonian is invariant under this transformation. So that seems like good enough to be a symmetry. What do we mean by symmetry when we first learn it in quantum mechanics or in quantum field theory? Someone hands you a Lagrangian. It's made out of some fields, phi. And you figure out some transformation on the fields phi. And you check if your Lagrangian, or more generally, if your action or path integral is invariant under that transformation or not. And if it is, that's probably good enough to be a symmetry. Here we work with a quantum Hamiltonian lattice model. We have a Hamiltonian. It's made out of the operators z and x. And you check that at G equals to 1, it is invariant under this transformation. How can it not be a symmetry? But if you think about it, or if you want to ask Mr. Wigner whether this is a symmetry, Wigner will say the following. Wigner will say a symmetry has to be implemented by a unitary operator. So Wigner will say there better exist a unitary operator, U, such that U xj, U inverse is zj plus 1. But the moment you roll down this equation, you realize that there's a contradiction. And let's try to get to that contradiction. The contradiction is that now you can consider U acting on eta. And remember, eta is the defying Z2 symmetry of the Ising model. It's an on-side ordinary Z2 symmetry. It's the product of X but now you can just do the action, this unitary transformation on each of the individual X. Which according to our assumption give you Zj plus 1. But importantly, we work on a closed periodic chain. And each Zj will appear exactly twice. And the Zj's commute with each other. So this expression, after you take the product, is just 1. But that means your eta is also 1. Which is clearly a contradiction as an operator equation on your 2 to the L dimensional Hilbert space. Okay. Is this argument clear to everyone?
I think we have the Hilbert space by requiring that the data has to be equal to 1. That's okay.
Right, so as I predicted, as I wrote down the questions, the zeroth order condition will be the one that people usually want to relax. And then so you're absolutely right. If I make my Hilbert space smaller, then there would be a unitary operator that implements the transformation. However, that Hilbert space will no longer be a tensor product Hilbert space. It's a tensor product Hilbert space subject to a global constraint. There's a counterpart of this, the question you just asked. You can also make the Hilbert space bigger. And then there will also be a unitary operator that implements this transformation. But suppose I don't want to make the Hilbert space bigger or smaller. I really want to stick with my 2 to the L dimensional Hilbert space, which has a tensor product structure. Then this is the best you can do. Well, I haven't told you what's the best you can do, but this is a contradiction you will arrive. Yes, you're absolutely right. Yes, Louis.
So making it smaller is just gauging the Z2?
No, it's not. It's not. Because as we learn from the CFT language, gauging a discrete symmetry in 1 plus 1D conformal field theory is the same as doing the orbifold. Orbifold, importantly, consists of 2 steps. And I will talk about those 2 steps in the later on. The first step is to do projection. And the second step is to introduce the twisted sector. And both of them are essential to guarantee the modular invariance. We will see a lattice counterpart of that in just a little bit.
Okay. Yes. Related to the extended Hilbert space, if I consider an infinitely long open chain.
Good. So the question was about what if I work on an infinitely long open chain? So let me first start with a finite open chain and try to think about the infinite open chain as a limit. There is a very nice language to talk about a lattice system on infinite chain, but I'm not good at that language, so I'm going to view the infinite chain as a limit. But if you work on an open chain that is finite, then you wouldn't even have the Kramers-Wannier transformation that leaves the Hamiltonian invariant from the first place. The reason is because if you apply the Kramers-Wannier transformation twice, you take xj to xj plus 1. But if you're on a finite open chain, there will be a point where this transformation runs into an issue. So the symmetry that we will see will just be broken on the finite open chain. And I'll reserve my rights on anything about the infinite chain. Okay, any other question? Good. All right. So if there's a lesson to be learned from this simple reasoning, is that we should never write arrow in theoretical physics. Because when you write arrows, you don't really know what you are talking about. Do you mean an equation like this, or do you mean something else? In physics, we should try to write an equality. Having said that, in the rest of my lectures, I might still write arrows in some places, but I'll try not to. And please feel free to interrupt me if I do. Okay, so the question that we would like to ask now is that what would be the equalities for this squiggly arrow? We just learned that the equalities for the arrow cannot possibly be this. So what could it be? Okay. So what turns out to be the case is that you can write down this operator D. And know that I'm using a different font. And I'm just going to write it down for you now. And later on, I'm going to tell you its properties. And after that, I'm going to derive it. So let's do it in the reverse order. So first of all, it has a factor of root 2. There's a lot I can say about the root 2. And I might say a little bit more about it. But for now, it's just a normalization. And then there's a phase, which take this form. Again, I'm going to take it as a normalization. Later on, you will see if you change the phase here, it will make some of the equations more ugly. There's a factor of 8, which is actually related to a lot of things. In particular, it's related to the critical dimensions of superstring theory. In critical superstring theory, the critical space-time dimension is 10. But if you work in the Lycon quantization, you only have 8 transverse direction. And that actually is related to this 8. But we will not need that connection in this lecture. And then let me write down the rest of the factors. All right, so it's quite a mouthful, but first I'll give you maybe 10 seconds to write it down, and then I'll slowly walk you through this expression. Get a sip of water. All right. Okay, the first thing I want you to note is that each factor here, 1 plus ix over root 2 or 1 plus izz over root 2, is a unitary operator. That's something you can check in real time. Take the dagger and multiply it with the original factor, e equals 1. In fact, this can be written as e to the I pi over 4 times x. Okay, so this factor over here is a product of local unitary operator, and therefore it's a unitary operator. And this operator I'll denote by UKW. It's known as a sequential, well, it is a sequential quantum circuit. We don't really need this language. It just means that it's not a finite depth quantum circuit. It's a product of local unitary where the number of factors in the product scales linearly with the system. It's sequential in the sense that in each step as you do the product, you have a neighboring overlap between the factors. Like this one with j, and this factor with j, and the next one with j plus 1. Anyway, we don't really need this terminology. It's just a unitary operator.
The terms in the product don't commute, right? So is there some...
Good. Yeah, so when I first, I gave this talk maybe a few times by now. In the first time and maybe the second time, I always specify the ordering of the product. But then I realized no one was paying attention to that. So after the third time, I stopped dropping that explanation. But thank you for asking. So the factors don't commute. So by this notation, I meant j equals to 1 is on the leftmost, and j equals to 2, j equals to 3, so and so on. In the paper, we did specify that. Okay, any other questions? And that's related to the fact that it's a sequential quantum circuit where the order matters. Yes?
The L lattice point is special, right?
Very good, very good. We'll get to that. We'll get to that. That's an excellent observation. This expression, this UKW, does not appear to be translationally invariant. In fact, it is not. And I even wrote the exercise problem on that.
But it is not dependent on this choice of
I'll get to that in just a minute, but let me give you the quick answer. UKW is not translationally invariant. However, D is. Okay? Good. So all you have to know is that this is some unitary operator. Now, what is this factor? Eta, remember, is a Z2 operator. It's the simplest Z2 operator you can imagine on the lattice. 1 plus eta over 2 is a projection operator. All right, so up to the normalization factor that I ask you not to think too much about, this D is a product of a unitary operator with a projection. Projection, by definition, has a kernel. Whenever eta is -1, whenever you act on a Z2 odd state, the projection operator evaluates to 0. So this is a matrix with 0 eigenvalues. And therefore, the operator D has a 0 eigenvalue, has a kernel. So this D is a non-invertible matrix. So the word non-invertible doesn't mean anything fancy. For finite L, it's just a big matrix with a kernel.
So this U is what you will get if you just decided to restrict your space to at equals 1, right? And what you did is just you added this projective.
That's right. That's right. So if you restrict yourself to the Z2 even sector, you don't have to include the projection factor at all. And this operator U will do the job for you. But as I said from the very beginning, that I want to work on a tensor product Hilbert space that's of dimension 2 to the L. Then you really have to stick this projection factor. Okay, so now let me discuss the properties of this operator. Now, as already noted in the questions, let's first look at the unitary factor, this UKW. So I made it a homework problem. I think the calculation is actually quite fun, so I really encourage you to do that. So the question is to compute UKW xj, UKW inverse. Now, for most of the j, this gives you the correct answer on the nose. So you feel like you almost want to celebrate the moment you find this UKW. But then at one site, you'll find something interesting. At one site, the last site, it becomes okay. So for most of the site, it does what you want. But we know that that's too good to be true because of the earlier contradiction we derived. And at the very last site, it almost does what we want, ZL, Z1. However, it has this non-local factor. For all the other sites, the right-hand side is a local factor on the link between J and J plus 1. But for the very last one, it involves a non-local factor. And this reflects the observation that was made in the questions that this UKW is not translationally invariant. Indeed, there's nothing special about site number 1 on a closed periodic chain. And yet, I choose to take the product from j equals to 1. And for the very last factor, I did something different. There's no ZLZ1 term in the very last factor. So this UKW does not commute with the translation symmetry. And that's why we need this projection factor here. So let me, the moment you multiply by this projection operator, this factor is just eta. Eta can be replaced by +1, and the operator will implement the transformation you like. However, I cannot write down an equation that's dxj d inverse because d contains a projection. I cannot possibly take the inverse of d. So what replaces this equality, and what is the true equality behind this arrow, is the following. dxj is zj plus 1 d, and dzj, zj plus 1, xj plus 1. Okay? So the upshot is that these are the equalities behind the schematic arrows that we wrote in the beginning. This equation is very similar to the equation, to the incorrect equation we wrote here, except for the fact that we couldn't bring the d as a d inverse to the left-hand side. All right, and I should emphasize that this is true for OJ. Now, because this is true for OJ, right at g equals to 1, d commutes with the Hamiltonian. Right. Any question?
So now d commutes with d?
Good. The answer is yes, and I'm going to write down the full operator algebra in just a minute.
What about d zj?
Ah, very good question. You see, I purposely didn't write that. So the answer is that if you just compute d times zj, it cannot be written as the form. Let me just write it here. dzj does not take the form of some O operator times d. So in that sense, this operator d only acts nicely on the z2 even operator. It does not act in a nice way on the z2 odd operators.
Actually, I have a follow-up. So that will clarify. What do you mean by acting nicely? So we have a unitary. The usual rule is if you conjugate the local observable with the unitary, you're going to get the local observable.
That's right.
So here the definition is, since it's not invertible, it's different.
That's right. So by act nicely, I just meant, first, what do I mean by act? I cannot conjugate anymore. So what I can do is to bring the operator O1 past this d and cross my fingers and hope that it equals this with some other O2. But this is only true, this equality is only true if O1 and O2 are both Z2 even. Yeah. Any other questions?
Yeah. So does it mean that just O2 becomes non-local? Is that the...
It's more than that. So when this is when O is Z2 even. But when O1 is Z2 odd, what you typically find is that it just becomes something else. You cannot write it in this way. Yes?
What are the, like you said, because of Wigner's theorem, it can't be a unitary operator? Wigner's theorem would imply that we need a unitary operator. But then the operator that we get, that's information it is not unitary. So then what are we giving it?
Right. So when Wigner proved his theorem, he assumed that the operator preserved the norm or preserved the probability. Our operator doesn't do that. It has a kernel. So it annihilates some of the state. So we can argue all day whether we should call such an operator a symmetry or not. Some people, like Wigner, will insist that symmetry should preserve the norm of the state. But I'll try to argue later on that the moment we go to quantum field theory in general space-time dimension and many-body lattice model, that notion is too restricted. it's also useful to talk about conserved operators such as D that doesn't necessarily preserve the norm, but it really behaves in many ways like a symmetry.
But here you are not in quantum field theory, you are quantum mechanics on a finite remaining state. So, I guess the question is, so Wigner introduced these things because he thought that was a very useful thing. So, is this thing useful for finite n or for finite L, I would say?
Actually, I think in my lecture notes, there's a section that starts with what is it good for, and we'll get to that part. Yes. And you are right. For finite L, this is a quantum mechanics system. And in quantum mechanics, we can either follow Wigner's strict rule on what the symmetry should be, and then it should be a unitary operator. Or we can also talk about any operators in quantum mechanics that commute with the Hamiltonian. And in fact, you cannot really argue beside the point of probability preserving that the operator should be unitary, because there's no notion of locality in quantum mechanics. Locality only emerges as you take L to be very large, or to the infinite limit. So for finite L, it's a quantum mechanics problem. Wigner would say symmetries are implemented by unitary. If you talk to someone who is more from a mathematical background, they would say any operator that commutes with the Hamiltonian behaves like a symmetry. But the moment you take L to infinity, then you have a notion of locality. Then this operators like D, I will argue, really have some practical usefulness and should be viewed as a symmetry. And then the constraint is also more stringent as you take L to infinity, because the notion of locality will come into play. Any other questions?
So it's useful because it allows us to understand the continuum limit?
It will allow us to constrain the phase diagram as we take the thermodynamic limit.
Now on the closed chain, you also have some locality around sides, right? Does that count?
Yeah, but that's only meaningful when you take L to be very large, right? Well, if L is 5, what does locality mean? Yeah, so that was my answer to Slava's question. Any other question?
Yes. I guess the difference between this, even at finite L, and quantum mechanics is that here you do have a notion of defect Hilbert space, right? That's important, right?
Not well. So first of all, I haven't talked about defect Hilbert space, and I probably won't talk about defect Hilbert space. Second, the notion of a local defect Hilbert space is only again meaningful when L is very large, because the notion of a defect Hilbert space is that you modify the Hamiltonian locally around the site. But whenever you talk about the word local, that's only meaningful when you take L to be very large.
Any other question? Oh, yeah.
So some naive question, but can't you exponentiate D in order to generate?
Oh, good. Okay, so first of all, let me make it clear that usually for continuous symmetry, if I have a conserved charge, Q, for instance, we exponentiate it and we put some rotation angle in front in the exponent to make it a unitary operator. For discrete symmetry, we don't have to exponentiate it, right? You don't have the infinitesimal transformation for discrete symmetry. So what we are given is directly the unitary operator. So for instance, eta, which is somewhere there, eta is a unitary operator. You don't take the log, you don't take the exponential, that's what it is. You should view D as the analog of eta. So in a way, it's already exponentiated. Now, back to your question, if you further exponentiate it, the issue, again, will be that it will not act in a nice way, not even on the Z2 symmetric operator. So that's the notion of locality is something that I want to impose. Any more questions before I move on? Okay. So now we identify a set of operators that commutes with the Hamiltonian at g equals to 1. So that consists of the Z2 operator eta, the operator D as non-invertible, and the ordinary lattice translation. Now whenever you have a set of conserved operators, the first thing you should do is to close its algebra. Try to multiply them together and see what you get. So let's start with the easier one. Eta squared is 1. T to the L is 1. Eta and T commute with each other. Now, next, we can consider eta times D. But since D contains this projection factor, it just equals D. And that's the same regardless whether you multiply eta from the left or from the right. And as was already asked several times, D commutes with the lattice translation. The reason I put T inverse here is because this operator happens to be the adjoint of the operator D. So on the lattice, we see that the operator D is not self-adjoint. This is to be contrasted with the continuum one, where the curly D equals curly D dagger. Okay? Yeah?
Why is T squared equal to 1?
Sorry, say again?
Why is T squared equal to 1?
T squared, L.
Oh, T to the L.
Yeah, sorry. Okay.
What do you write? T minus 1 has to be T minus 1, not T.
Here? Yeah, it's T minus 1. But it's just a matter of convention. Because here, you know, D is kind of doing a half lattice translation in the positive direction. So if you multiply by T inverse, it's like doing a half lattice translation in the opposite direction. And that's what the dagger does.
Should one of them just be T?
Should one of the two?
No, sorry, never mind.
This dh equal to ht is valid only at g equals to 1.
Correct.
How is there a way to see that?
Oh, it's just because D exchanges the x term with the zz term, right? And G is the relative coefficient. G squared is the relative coefficient between the two terms. So away from G equals to 1, it maps the G greater than 1 phase to the G smaller than 1 phase. And that's what Kramers-Wannier is supposed to do.
This equation is still valid for any G. Just that has no.
Yeah, that's true. So what I really meant is that at G equals to 1, these three operators commute with the Hamiltonian. But you are absolutely right. Let me just erase this to make everyone feels better. That's the nice thing about working on the lattice, right? We just talk about operators. We don't even have to talk about Hamiltonians. But the Hamiltonians give us a guiding principle to look for operators that are of interest to us. Okay? Well, I haven't got to the, I think, the most interesting equation, which is what happens when you take D squared. Okay. Now D squared, since it contains a projection, it will again contains the projection. But because D is kind of doing a half lattice translation, its square will contain the lattice translation. Now, I haven't derived this, but in the rest of my lecture today, I will derive this. What else do I? Oh, sorry, let me just make one more comment. So already here you see that, and that was back to your question, we don't quite get the algebra in the continuum. On the lattice, there is an effect of mixing with the lattice translation. The curly D in the continuum is an internal symmetry. And what do we mean by internal symmetry in the continuum? It means that it's an operator that commutes with the stress energy tensor. On the lattice, we don't have the full SO1, Lorentz symmetry. But the operator algebra of D actually involves the lattice translation. As you take L to infinity, lattice translation by one side is doing very little. So as we take L to infinity, the lattice translation by one side operator becomes 1 in that limit. And this factor drops out. And in that limit, D equals D dagger. But if you work with a finite size system, there's a mixing with lattice translation. There was a question early on. Yes?
So in the continuum, one could have read this equation as D dagger.
Very good.
Yes. Yeah.
So that equation is still true. So on the lattice, D times D dagger or D dagger times D is still 1 plus eta. So you can say that the modification is really in this equality. It's equivalent. Yeah, thank you. Okay. Okay, so that's the answer for the question we pose. these are the properties for the operators I define. And now for the remaining 30 minutes, I'll try to derive or explain where this operator comes from. There's more than one way to derive it. I will present one particular way. And after the lecture, I'll be happy to talk about other ways to derive it.
Yeah, very stupid question. Is that easy to say D is half lattice translation from the formula?
Okay. So I think half lattice translation is an ambiguous term. In fact, the precise way to make the precise meaning to call Kramers-Wannier a half lattice translation is this equation. Right. So on a spin chain, right, you have L site. What does it mean to do half lattice translation? There is an unitary operator which square to t. The precise meaning is that there's an operator d which will square to the projection times t. Yeah. But intuitively, the reason we refer to it as a half lattice translation is because xj is on the size j. zj plus 1 is kind of on the length between j and j plus 1. So that's why it behaves like a half translation. Yeah.
So it's also like Jordan-Wigner half translation.
I'll get to that in just a minute, yes.
If you have a regular symmetry and you apply a projection next to it that kills half the states, it would be a non-invertible symmetry, but it would be a boring one, right?
Absolutely.
What the super distinguishing factor between
the distinguishing factor here is that UKW is not a symmetry.
So, okay.
UKW, right? So at this point, you can stop. You could have stopped me, and well, actually, that was the reason I talked about this. You could have said that, why don't I just work with UKW? You know, I want to work with something invertible. But then the price you pay is that UKW does not commute with the Hamiltonian. And he also acts in a funny way on one of the local operators, one of the Z2 even local operators. So for ordinary symmetry, as you said, you can always multiply it by a projection or just consider projection itself. No, that's a valid symmetry commutes with the Hamiltonian. But there it's made out of unitaries that do commute with the Hamiltonian. Here you really cannot live without the projection, and that's the distinguishing feature of this operator D.
Another question. So once you take the continuum limit, so what's this curly D should have some nice property in some sense. It's like local observable. So what is this nice property? Does it have a nice property?
So in the continuum, I would say the nice local property is that curly D can be represented by a topological line in Euclidean spacetime.
Can you say it in Hamiltonian?
In the continuum or on let me try to say it. Okay, yeah, I think I can say that. In the continuum, it means the following. It means that I will be able to use this curly D to twist my Hilbert space and define a new Hamiltonian with the twist. And that Hamiltonian has to, what I meant is that think about this as a space-time torus. If I insert curly D here, this is a Euclidean partition function, but it emits a Hamiltonian interpretation if I choose this to be the time direction. I have to be able to write this as a trace over some Hilbert space with a nice Hamiltonian factor here. And this imposes a non-trivial constraint on what this curly D could be.
But here, curly D is not an operator on Hilbert space.
Here is not an operator on the Hilbert space because.
So even though it's interpretation, it's not interpretation as an operator on Hilbert space.
Sorry, say again?
Even though it's an interpretation Hamiltonian terms, it's an interpretation of defect D in Hamiltonian terms. It's not an interpretation as an operator in Hilbert space.
It's not an operator on the Hilbert space.
So this D in those equations, I shouldn't think of it as an operator in Hilbert space.
There are two ways to view the curly D, either as an operator acting on the original Hilbert space, or as an object that gives you a different Hilbert space, H sub D.
But I'm just wondering, so when I have a unitary operator, I usually want it to be not just some random unitary operator in Hilbert space, but some something which preserves locality. When I conjugate some local observable with it, I get something local again.
Yeah.
Just approximately.
Yeah.
So D, this one, if I think of D as an operator in Hilbert space, doesn't have any nice property relative to locality as an operator in Hilbert space.
Good. So you're asking, is there how do I see the notion of locality for this curly D?
Yeah, but if somebody hands me, say some operator, it says it's nice operator as an operator in Hilbert space, and I'll say, well, how do I check that?
Right. So do you want the continuum answer or the lattice answer? The continuum answer. The continuum answer, I will argue, is that in space-time, it should be characterized by a topological line operator or defect, such that any correlation function that involves this object only depends on the locus or the homotopy class of this defect. That's the notion of locality. It's not some spread out thing. It only depends on where you insert this line. That's in Euclidean language. I can also try to say it in the Hamiltonian lattice language. In the Hamiltonian lattice language, which is the picture I'm not saying in this lecture, is that every symmetry should give you the following two objects. First, it should give you a conserved operator that commutes with the Hamiltonian. That's the D I presented here. But that's only half of the story. The other half is that it should give a defect of the Hamiltonian lattice model. And what do I mean by a defect? By defect in a Hamiltonian lattice model, I mean I modify the Hamiltonian locally around the site. And the defect and the operator should be related in some ways. And that was the discussion we had in the middle paper there. And really, it's this existence of a local defect that distinguishes this D from all the other operators that commute with the Hamiltonian.
So there's no simple way to characterize locality of D just on its own in the modern operator.
This is the best way I can think of at this point. Later on, we'll give a different expression for the operator D. And I really meant the operator, not the defect, such that the notion of locality is kind of manifest. But I don't know if I don't know the full story there. The best I can say at this point is the existence of a local defect in the Hamiltonian lattice language. And if you push me to the continuum field theory, I have to resort to the Euclidean space-time picture.
The fact that it acts nicely on a bunch of on a large class of local operators, that's not enough.
Well, I was very tempted to say that, but then then people can ask me, what about the other class? What about the complement of the operator?
So in the continuum, it feels like this defect picture relies on like some Lorentz invariance, but if I just have continuum but no Lorentz invariance, can you use some? Is there another way to say it?
I don't know the answer to that question. Yeah, I think that's a good question. But on the lattice, there's some relation between the defect and the operator because you can move the defect. So if you start with a defect, you can kind of make it an operator, and that's the closest I can get. But indeed, the constraint is the strongest when you work with a Lorentz invariant quantum field theory.
Shu-Heng?
Yeah.
So can I understand the locality constraint on the level of lattice as your defect to be able to be defined, to act locally on the spin chain as opposed to on the whole spin chain?
So I wouldn't use the word defect acting locally on the operator, but well, so then this is
that's how I can create the defect point if I allow my operator to act not on the entire spin chain, let's say just on the part of the spin chain.
Well, but this D does act on the entire chain. Right?
No, but I mean, so you said there are two pieces of information associated with the defect in the Hamiltonian lattice model to ensure it's a local defect. So one piece is this D that you define to act on the entire spin chain, but the other piece of information can I understand it as being able to define D acting on a part of the spin chain.
Good. So there will be expression for D where you kind of have that. Here you can see that maybe this is the local factor of D, but I don't have a uniform way to explain it.
But that's one way to create the defect point.
To create.
But being able to act, have a notion of D that acts like on part of the spin chain, you can create a defect point by,
I don't really know how to do. I can do that on an infinite chain, but on a closed chain, I don't know how to do that.
It will create a pair.
Even on a closed chain, I don't know how to do it to create a pair. because of the non-unitary nature. Okay, yeah, I try not to talk about the defect too much, but I agree, it's very important for the notion of locality. All right, okay, I think I should just move on. Otherwise, I can continue taking questions. Okay, so I should at least talk about how to derive this operator. So to derive it, there are several different ways to derive it. And to derive it, the derivation I'm going to give we'll be using a different model that's based on fermions. So now I'm going to work with a different space where I have two L sites. I'm going to use little l to label the site. On each site, I will have chi L, a real Majorana fermion, a real Grassmannian variable. So it's basically the same setup that Max discussed in his lectures. And they obey the standard Clifford algebra. Now, since I have two L sites, and a pair of Majorana fermion will give you a two-dimensional Hilbert space, the Hilbert space for this system is still 2 to the L dimensional. But this is a different system now. The Hamiltonian I'm going to consider, actually there are two of them. So for H plus, I impose this corresponds to the periodic boundary condition for the fermions. For H minus, this corresponds to the anti-periodic boundary condition for the fermions. Okay, so bear with me. This is a different model, but this model will eventually lead us to the operator D. Now, this is a little bit different from the model that Max discussed, because I have the nearest neighbor interaction between every pair. Between the even and the odd, and also the odd with even. The Kitaev chain will correspond to the deformation of this, where you only keep the even, odd, or alternatively, odd, even, so on and so on. So the Kitaev chain corresponds to the massive fermion, but this one actually corresponds to the massless Majorana fermion. But let's not talk about the continuum and just focus on the symmetries. And this time, don't worry, every symmetry will be invertible in this model. So there's a symmetry that's -1 to the F. That's a fermion parity symmetry. You just flip the sign of every Majorana fermion, and it can be written in the following way. It's the product of all the fermions with a phase factor that I put in for convenience. This factor is inserted so that -1 to the F squares to +1. And this is obviously symmetry for both H plus and H minus. There's another symmetry, which is the Majorana translation. When you pick the plus sign, obviously, this Hamiltonian has that symmetry. But if you pick the minus sign, even though it doesn't look like it has the symmetry, you can modify your operator T minus such that for most of the site, you just shift the fermion by one site, but for the very last one, you flip the sign. And you can easily check that that's still a symmetry. Okay, so these are two invertible symmetries of the Majorana model. And there's one interesting thing I want to talk about the algebra there. So let's say we take H plus. And as Stemson was commenting, I shouldn't really refer to the Hamiltonian when I talk about operators, but the Hamiltonian give a nice guiding principle for what kind of operators will be of interest to us. For H plus, I want to focus on -1 to the f and T plus. And in particular, I want to compute this algebra, T plus -1 to the f, T plus inverse. And this is a computation we can do in real time together. Okay. And each T plus, just take, so it takes chi1 to chi2, chi2 to chi3, chi2L to chi1. But now, to bring it back to the original form, you would like to move the very last chi1 to the beginning. But note that we have even number of fermions here, so there are odd number of fermions in front of this chi1. And that gives you a minus sign. And that's an important minus sign that will be relevant to the non-invertible symmetry later on. It means that this naive lattice translation for the Majorana fermion actually anti-commutes with the fermion parity. If you work with the anti-periodic boundary condition, then it's easy to convince yourself because you get an extra minus sign, they end up being commuting. Yeah?
Can I view that as like a LSM type of thing?
Yeah, I think people in the literature have interpreted it as an LSM type anomaly. It does correspond to an anomaly in the continuum massless Majorana fermion. So let me comment on that. So the continuum limit of this model is a free Majorana fermion. Is a massless Majorana fermion, importantly. And the massless Majorana fermion has true Z2 symmetry. It has a -1 to the f left, which only flip the sign. And as I promised, I will break my promise that I'm going to write an arrow here. So the continuum Majorana CFT has two Z2 symmetry. One that flips only the sign of the left moving guy, the other that flips the sign of the right moving guy. But if you look at the lattice model, we only see a single fermion parities, -1 to the f. So what ends up happening is that the lattice translation T will become the chiral fermion parity in the continuum limit. And the product of these two is the -1 to the f over there. And in the continuum, this H plus will correspond to putting the periodic boundary condition for both side left and side right. In the string theory language, that corresponds to the Riemann sector. H minus, on the other hand, corresponds to the Navier-Schwarz sector. And in the continuum, you can show that in the Riemann sector, -1 to the f and -1 to the f left anti-commute. Whereas in the Navier-Schwarz sector, they commute. And this minus sign corresponds to an anomaly of the Z2 cross Z2 symmetry in the continuum CFT. And that's the same anomaly telling you why when you do GSO projection in superstring theory, the number of transverse direction has to be a multiple of 8. But on the lattice, you only see a mod 2 version. Okay, so I have 5 minutes left. Oh, I have another blackboard. Okay, so why do we talk about this different lattice model, the Majorana fermion model? The reason is because usually we say Ising equals Majorana. But that's true for 99% of the time, but it's the remaining 1% that will be relevant for the non-invertible symmetry. And what do people usually mean by this? What do people usually mean by this on the lattice is that you can do a Jordan-Wigner transformation by pairing up the Majoranas. Okay, so what's happening here? We know the Majoranas obeys the Clifford algebra over there. Here, sigmas are some Pauli matrices. So here I pair up the Majoranas into the odd side and the even side. And for each pair, we do this change of variables to make it to write it in terms of the Pauli matrices. The Pauli matrices obey their standard Pauli algebra. The gammas obeys their Clifford algebra. And the non-trivial statement of these two equalities is that the two algebras are compatible with these two equalities. So that you can easily check. The important thing here is that a local fermion operator is mapped to a non-local operators of the Paulis. So the transformation is not a local transformation. In fact, it corresponds to gauging, as we will discuss maybe next time. Now, if you do this substitution of variables, chi's, into the Hamiltonians there, this is what you will find. All right. So before I close the lecture today, let's just take a look at the Hamiltonians written in terms of the Pauli matrices. So these are literally the same Hamiltonian H plus and H minus as the one over here. But now we just do this change of variables to write them in terms of the Pauli matrices. For most of the terms, again, you see that it's the same as the critical Ising model. But again, there's one mistake at one link. And at this link, you have this operator minus 1 to the f, which involves all the fermions field. So it maps a local Hamiltonian in terms of the fermions into something that's non-local in terms of the Paulis. In fact, written in terms of the Paulis, minus 1 to the f is a product of the sigma z's. And this is why there's a question mark above this equality. Yeah, next. Oh, sorry, it's X. Thank you. And that's why there's a question mark above the equality. It means that they're almost the same, but they differ in this one term. And the reason we talk about the Majorana fermion is because we want to understand a symmetry in the Ising model. And it has a nice, simple origin in the Majorana system. But to really nail down the symmetry globally, we have to fix this question mark. And that's what my next lectures will be. But before that, let me pose a question to conclude the lecture today. If you forget about this question mark, you say, I don't care about this one mistake on the entire chain. I'm just going to assert that the Ising model equals the Majorana fermion models. Then you run into an immediate contradiction. In the Majorana model, you have the lattice translation T plus. But note that on the Majorana system, you have 2 L sites instead of L. And this T plus, in particular, is 2L's power is 1. But in the Ising model, you only have L site. You have a ZL symmetry that's implemented by the operator T. You don't have a Z2L symmetry. So what happens to this guy? What happens to this T plus? So just by comparing the symmetry, you know the 2 models cannot be globally the same. And that global difference is what's going to lead to the non-invertible symmetry D. All right, I'll stop here and continue next time.